Good morning, student. I welcome you in the third session of your B.Sc. B.Ed chemistry courses, and this is the part third. And today I will discuss a very simple topic, that is Ostwald's dilution law. In my first lecture of this electrochemistry, particularly electrolyte conductance, I discussed about the fundamental aspects, and in the second part I also discussed the relationship between the molar conductance, equivalent conductance, as well as the observed conductance. I also discussed the effect of dilution on the observed conductance, specific conductance, as well as the molar conductance. Now, in continuation of that lecture, now I will explain one of the very simple but very important theory, that is called the Ostwald dilution law. And of course, the name itself is a definition. You can see that it is related to the dilution as well as the concentration of the electrolyte and dissociation constant, etc. Now, before I go into details of this topic, I must tell you the importance of this Ostwald dilution law. And it was discovered by the great scientist Ostwald, and there are a large number of very good articles available in the literature, and I am taking one such article, and it is related to dilution effects. But of course, you should mind it that it is related to the weak electrolytes, and the general formula of Ostwald dilution law is, you can see here, it is a dissociation constant, and this alpha I have already discussed in my second lecture. I will again discuss with these things, that is called the degree of dissociation, and C is the concentration. So the formula is like that. So whenever I am talking about the degree of dissociation, I must mention the monumental contribution of the Arrhenius, because that Arrhenius first time developed this partial dissociation of that electrolyte. So therefore, I will just explain one or two points of that Arrhenius contribution. And again, I am seeing one of the very important paper published in the Resonance 2012. It is a general contribution, and if you want to learn about this Ostwald dilution law or the actual role of Arrhenius, you must William Ostwald, and we consider him the father of the physical chemistry. So you can understand, आपको समझ में आ रहा होगा कि ये Ostwald dilution law कितना महत्वपूर्ण है. Now, अभी थोड़ी देर पहले मैंने आपको बताया कि जब भी हम Ostwald dilution law को पढ़ेंगे तो सबसे पहले आपके दिमाग में आएंगे अल्फा, that is the degree of dissociation, and that degree of dissociation was developed by that great Nobel laureate. His name is Arrhenius, because in 1903 he was awarded Nobel Prize for the simple dissociation work. So that Ostwald dilution का नियम degree of dissociation के ऊपर भी based है, and he has taken the help of this degree of dissociation as well as the law of mass actions. So, and then he combined that equations and derived that Ostwald dilution law. Now, as you know that there are two types of electrolyte. One is strong electrolyte, another is the weak electrolyte. And today I am concerned about the theories of the weak electrolyte, like acetic acid, like that. So, of course, he has derived this equation is 1899, but before that Arrhenius is also discussed this theory of ionization or sometimes the dissociation, and the just value of alpha is, you know, that it is the equivalent conductance or molar conductance as particular concentration divided by equivalent or molar conductance at infinite dilution. आप जीरो भी लिख सकते हैं, जब हम डिराइव करेंगे हम उसको अल्फा लिखेंगे. नाउ लेट मी derive these things, but before that, if you listen my lecture yesterday carefully, when we plot a graph between the molar conductance and concentration of the square root of the concentration of that electrolytes, so the nature of the weak electrolyte and strong electrolytes are entirely different. इसके लास्ट वाले लेक्चर में मैंने आपको वैल्यूज़ बताया था कि डिग्री ऑफ डिसोसिएशन का वैल्यूज़ भी मैंने आपको बताया था. मैंने आपको ये भी बताया था कि जैसा जैसा हम सॉल्यूशन को डाइल्यूट करते जाएंगे मोलर कंडक्टेंस जो है बढ़ते जाएगा. बट द ट्रेंड्स फॉर स्ट्रॉन्ग इलेक्ट्रोलाइट्स आर नॉट वेरी प्रोमिनेंट, वेर एज इफ इट इज ए वीक इलेक्ट्रोलाइट यू सी देयर इज ए डेफिनाइट ट्रेंड्स. एंड एक इन्फाइनाइट डाइल्यूशन में एक ऐसा समय आएगा जब आपका मोलर कंडक्टेंस और इक्विवेलेंट कंडक्टेंस कांस्टेंट हो जाएंगे, तो उसको हम लोग बोलेंगे इक्विवेलेंट कंडक्टेंस और मोलर कंडक्टेंस एट इन्फाइनाइट डाइल्यूशन. सो नाउ व्हाट इज द एक्चुअल डेफिनेशन ऑफ ओसवाल्ड डाइल्यूशन लॉ? सो द ओसवाल्ड डाइल्यूशन लॉ इज ए रिलेशनशिप, मैं अभी आपको समझाऊंगा, रिलेशनशिप बिटवीन द डिसोसिएशन of a weak electrolyte, and it relates the degree of dissociation and dissociation constant. If you ask me, sir, what is the most important application of this Ostwald dilution law? I will tell you that with the help of this Ostwald dilution law, you can determine the dissociation constant of any weak acid or base. और आपने जब आप एमएससी में आएंगे, क्योंकि आप अभी बीएससी अंडर ग्रेजुएट के स्टूडेंट हैं, जब आप एमएससी में आएंगे तो हम आपको ऐसे एक्सपेरिमेंट कराएंगे यूजिंग डिफरेंट सॉल्यूशन ऑफ एसिटिक एसिड, जिससे आप डिसोसिएशन कांस्टेंट निकाल सकते हैं. और आपने इस पहले जो पार्ट 2 में देखेंगे, जब हम आपको डिग्री ऑफ डिसोसिएशन की वैल्यू बताए थे, फॉर वीक इलेक्ट्रोलाइट इट इज़ ऑलवेज लेस देन 1. तो आप समझ गए होंगे कि देखने में ये बहुत स्कूल लेवल से आप ओसवाल्ड डाइल्यूशन लॉ पढ़ रहे हैं, पर ये बहुत ही इम्पॉर्टेंट है, क्योंकि विलियम ओसवाल्ड को भी 1909 में नोबेल प्राइज़ मिला था, और इनकी जो दिस लॉ इज़ बेस्ड ऑन दैट आर्नियस डिसोसिएशन एंड ही हैज़ आल्सो अवार्डेड नोबेल प्राइज़. तो आप समझ सकते हो कि ये इतनी सिंपल कंसेप्ट है, बट ये बहुत ही इम्पॉर्टेंट कंसेप्ट है. अब मैं इसकी डेरिवेशन आपको बताऊंगा. ओसवाल्ड डाइल्यूशन लॉ को डिराइव करने के लिए मैं एक सिंपल इलेक्ट्रोलाइट्स ले रहा हूं, दैट इज़ वीक इलेक्ट्रोलाइट्स, एंड दैट वीक इलेक्ट्रोलाइट्स एट रूम टेम्परेचर इट डिसोसिएट्स इनटू हाइड्रोजन आयन एंड द A ion. So I can take a particular reaction, that means I can also take the acetic acid also. Let me explain these things. Now I can use acetic acid and acetate ion, or it is better to take HA. And we assume the concentration is capital C, or you can use moles per liter. You can use that sense. And if you, what I have told you, that it is a relationship, and equilibrium constant can be written as like that. So it is a relationship between the K and alpha. So that is very important. Alpha is degree of dissociation. Suppose I am taking before the equilibrium, when there is no dissociation, suppose there is a C moles per liter, and there is no question of dissociation. But at equilibrium, you can write alpha. You can write alpha. Or because the concentration is C, so you can write like that. So at equilibrium, it is 1 minus, very, very simple concentration is C, like that. And it is C alpha. C alpha. So, say very school level derivation, K is equal to, you know, that C square alpha square. You know, it is like that. So 1 minus alpha C. So this C is cancelled. So the final equation, write in the red color, that Ka is equal to alpha square C 1 minus alpha. So that is the Ostwald dilution law, and so K is related to alpha C 1 minus alpha. You know that C number of moles per unit volume, so C is equal to 1 by, one can write 1 by V also. So one form you can also write alpha square, alpha 1 minus alpha V, but better it is, you should write like that. So now just I want to take a relationship between K and alpha. So what I do, so मैंने अभी आपको बताया कि ओसवाल्ड डाइल्यूशन लॉ में डिसोसिएशन कांस्टेंट और अल्फा का रिलेशनशिप है. एज बिकॉज इट इज अ वीक इलेक्ट्रोलाइट एंड इट डिसोसिएशन वैल्यूज इज लेस देन 1, बहुत ही कम वैल्यूज है, तो आई कैन एलिमिनेट 1 माइनस अल्फा. बराबर इसको. सो आपके पास क्या बचेगा? के, I'm sorry, it is alpha square. So alpha square C 1 minus alpha. So as because अगर ये बहुत डाइल्यूट है तो वीक इलेक्ट्रोलाइट है, तो ये हो गया अल्फा स्क्वायर C. That means that dissociation constant is related to the concentration. और मैं अगर ऐसा लिखूं, अल्फा स्क्वायर इज इक्वल टू K divided by C. So alpha is equal to under root of Ka divided by C. That means the degree of dissociation is inversely proportional to that concentration. So that is the one term. Now the second part is that is called the validity or verification of Ostwald dilution law. Now I am discussing the validity of the Ostwald dilution law. You have seen the application, that means we can determine the dissociation constant of any weak electrolyte using the various values of ionic conductance or even molar conductance like that. But you can also prove the Ostwald dilution law using a very simple formula, because we know that alpha is equal to equivalent conductance a particular dial or equivalent conductance at infinite dilution. Or even in some books you can write, there is no problem, molar conductance can also be written like that, capital letter, molar conductance also. So, of course, in some cases I can directly write K is equal to alpha square C, because for weak electrolyte the value of degree of dissociation is very less than 1. But you can use, there is no problem. Like if I write like that, we know the value of is V capital alpha square, C divided by 1 alpha, or just here I can write lambda infinite. So it's very simple. K is equal to, so E square C divided by 1 minus V to infinity, and of course you can write it here also square. So that can be written as like that, square. Now if I write here, so it is lambda square minus V and lambda infinity, because equal to K. Or what I can write? I can write K multiplied by this alpha square, for C is here, minus you multiply with this K lambda V lambda infinite is equal to lambda V square and C. Now this whole equation is divided by K lambda V and lambda infinite. So you just write like that, K V lambda, of course it is actually this is square, so it multiplied by the square. Then again K V lambda infinite square, this divided by K V square. Just this K cancel, this cancel, this K cancel, this V cancel, this cancel, this cancel. So what I can write? Here you can see 1 divided by molar conductance or equivalent conductance minus, everything is cancelled, 1 molar conductance at infinite dilution is equal to molar conductance C divided by K alpha square. If I slightly rearrange this equation, 1 V is equal to 1 lambda infinite plus C Ka square. So you all know the straight line equation, that means y is equal to mx plus c. So if I plot a graph, between one by molar conductance or equivalent conductance at particular and C. Suppose you have taken 5 solutions like 1, 0.1, 0.01, 0.001, 0.0001 acetic acid solution and measured their equivalent conductance or molar conductance at particular direction. So you are getting 5 values, different concentration, you will get a straight line. So if you are getting a straight line, that means the Ostwald dilution law is complied. So, and if it is mx, so this is slope will be Ka and infinity square like that. And intercept, you know, this is the intercept. So with the help of intercept and slope value, you can also calculate the dissociation constant or the molar conductance or equivalent at infinite dilutions. So this is this very simplest method for the validity of the Ostwald dilution law. Or even you can also calculate like that. You can directly write this value of K in the infinity square, K is equal to, of course, C. So by that method also you can calculate these things. So let me summarize the things. Today I have discussed the very simple equation of your B.Sc B.Ed, that is the Ostwald dilution law. As because you will become a teacher, so I have given some special type of equations, because you know that is a very simple equation. From the school level you are learning these things, but you know that the dissociation and ionization is very important. So therefore, I also discussed something about the Arrhenius equation regarding the dissociation. So in a nutshell, Ostwald dilution law is the relationship between the molar conductance with the concentration, or even you can call it the degree of dissociation is inversely proportional to the concentration, like that. And because the limitation of that Ostwald dilution law is that it is only valid for weak electrolyte. So next time we'll discuss about the strong electrolyte, like Debye-Huckel theory. So this is the part 3, and part 4 will be the Kallol law. So I think you have got a very clear-cut idea about the Ostwald dilution law. Thank you very much.